Thanks, Aman. So today I'm going to be giving a talk on work that I've done throughout my PhD on input scheduling under constrained dynamics and receding horizon control with uncertain preview. So this has been work done in collaboration with my supervisors, Michael Cantoni and Aman, and it's been supported by the Australian Research Council in partnership with Rubicon Water. So first I'm going to give an introduction and a discussion of the high-level problem that we're looking at here. And then I'll present a motivating application that will lead to two problems that are explored in this work. The first is rigid profile input scheduling, which I'll briefly outline the problem and our approach before spending a bit more time on the second problem, that is constrained receding horizon control with uncertain preview. So in the setup that we're looking at here, we have a dynamical system that we're denoting P that operates in an environment that we're denoting E. The dynamical system has two inputs, this control input U, that's going to be determined by some controller, and then this second input dt that is determined by the operating environment. The dynamical system has some output that's the measured state, xt. So in the setup that we're considering, the environment can actually be influenced, and we're going to denote that influence signal calligraphic N, and it can be influenced into how it generates this disturbance dt. So there's some control over this through this influence over the environment. So later in the talk, I'll present an application that fits such a model. So in the setup that we're considering here, the primary objective is constraint satisfaction, and that is that we're given a time horizon calligraphic t and a set of constraint sets, and then we want for all time in the time horizon the state, the control input and the disturbance input to be inside this constraint set. Now this time horizon could be infinite, so for example it could be the set of all natural numbers if it was in discrete time. So we might also have some secondary objectives that relate to performance optimization, and these could include minimizing the running cost of the dynamical system P and minimizing the cost incurred by the operating environment E. So these secondary objectives may be in conflict with each other, so the best outcome for the dynamical system may not be the best outcome from the operating environment perspective. So it might be important to consider how we might manage that potential conflict. So that leads to our high-level problem, and that is, given some uncertain information about the environment, design the control system to meet the primary objective of constraint satisfaction with consideration of the secondary objectives, that is performance optimization. So there's two parts of this setup that are a little bit non-standard, and the first is that we have this ability to influence the environment, so that has this, influence how we might generate this disturbance through this signal calligraphic N. And the other part is that the control system has this uncertain information about how the environment might react to this influence, and it might be able to use this to make more informed decisions on this control input U. So the approach that we're going to take is to break down the two mechanisms of influence into a control hierarchy. So the first mechanism that sits at the top layer, we're going to call the scheduler. And the scheduler's primary role is to exert influence over the environment E through this signal N. The second or middle layer of the control hierarchy we're going to denote the controller, and its primary role is to steer the dynamics of P through those constraint sets using a model of how the scheduler has this influence over E, and that's going to be this interface here. Within this control hierarchy, we're denoting that the dynamical system P is the bottom layer. So this dynamical system could represent an open loop system, or as we'll see in the motivating application presented shortly, it could also be a low-level closed loop system. So going into more detail of the components, so the first component, the top layer component, is the scheduler, and it has two inputs and two outputs. The first input is these constraints and preferences from the operating environment that the scheduler then uses to generate an influence signal to the environment that the environment will then use to generate these disturbances dt. The second output from the scheduler is this model of the uncertain response of the environment to this influence. So the environment will respond to this influence, generate something that may not be exactly what the influence was, and this is a model of that uncertainty. And then it has this second input that comes from the controller, and that's going to, as we'll discuss later, constrain the future evolution of this uncertain model of future disturbances. So as an example, this WT could represent a tube of all the possible realizations of the disturbance relative to some nominal. So the controller receives this uncertain model of future disturbances from the scheduler as an input, along with a real-time measurement of the current disturbance input, which we're assuming is going to be measured in this context, and a real-time measurement of the current state of the system. It then generates as outputs the control input to the dynamical system, which is used to steer the dynamics of P through the constraints. And this signal FT to the scheduler, which, as we alluded to, will be used to limit how the scheduler can provide future instances of this model of uncertain future disturbance, the model of future disturbances. So putting everything together, and we can see the control hierarchy here again. And these layers all have different but interlinked roles with the primary objective of achieving constraint satisfaction of the inputs and outputs of this dynamical system. The layers may also operate on different timescales. So for example, the bottom layer may operate much faster or more frequent timescale than the top layer. And that's indicated that the fact that these signals have different indices here. So in this work, we focus on the development of two optimization-based approaches to designing aspects of the scheduler and the controller. And we'll pay special attention to try and make sure that both the approaches and the implementations lead to tractable optimization problems for realistic size systems. So now let's look at a motivating application from open channel irrigation networks. So here the dynamical system is a channel of interconnected pools, where each pool, as depicted here, consists of an upstream gate, a downstream gate, where the upstream gate regulates the flow on the basis of low-level feedback control on the basis of the water level depth and flow at the downstream end of the pool. The low-level control has an input that is a water level reference, which is linked to the capacity to supply, capacity of the outlets to supply flow under the power of gravity, and hence this water level reference actually provides a more suitable interface to a higher layer in the control hierarchy. So the farmer's outlets here act as the uncontrolled but measured disturbance, and we'll be able to provide some influence over this. And the constraints in this system are limits on how much the gates can open and close, and also limits on how high or low the water levels in each pool can go. So the overall dynamical system is a cascade interconnection of pools, and aligning with the notation that we've already introduced, the water level references for each pool make up the control input U, and the offtakes or outlets to the farmers in each pool make up the disturbance input D, and the levels, flows, and the local controller states make up this state X. So in this application, the operating environment is the users of the system. For example, the farmers that request or take water through their outlets. So the information that the scheduler knows about the environment consists of a rigid profile load input for each user. And that is, the farmer will only take flows that adhere to this flow shape. So this might be an example of what a farmer requests, and they will, can only take something that adheres to this shape, which means that the flexibility for the scheduler is that they can only shift these orders in time. They can't change the shape of them. Each user also submits a sensitivity to shifting its request. And there may also be limits on when the farmer can actually start or they're taking their water, and we'll call these limits the shift intervals. So that leads to the role of the scheduler, which is sometimes called the planner in this application. And that is, given this set of information about the environment, generate a nominal schedule, that is the set of shifts, to minimize a social measure of sensitivity to deviation of requested delivery time, while ensuring responsive P to the scheduled offtakes is within constraints for the entire scheduling horizon, and the scheduled shifts are within the bounds. So this is the first problem that we look at in this work, and I'll discuss a bit more about that shortly. So after generating a nominal schedule to the environment, the actual environment may respond to this nominal schedule, but there may be some uncertainty in how it responds. So, for example, the farmer may actually start their outlet slightly early or slightly late than the scheduled time. Or perhaps the flow rate through the outlet, which might depend on the topography of the land, is slightly more or slightly less than the scheduled amount. So that leads to the role of the controller, which is to provide robustness to this uncertainty. So it has access to the model of the uncertain model of the schedule influence over the environment, that we're denoting this calligraphic W. And it also has access to the real-time measurement of the disturbance. That is, we have measurement of the outlet flows and real-time measurement of the state. So that's because there's, sensors and at each of the regulators in the system. The aim of the controller is to determine suitable water level references and an interface to the schedule that ensures the system remains within constraints. Now, since this problem has constraints and uncertainty, that motivates us to use a common approach of robust receding horizon optimal control to synthesize such a controller. So it also leads to two key questions. And the first question is, how can this model of schedule influence be allowed to evolve across time? So if the system's operating very close to the constraints, it seems unreasonable that the scheduler would be able to schedule all possible options in the future. So how would the controller constrain what the scheduler can do in future instances? The second question is how to manage the balance between the scheduler and control objectives. So for example, in this irrigation application, the users of the system might all want their orders to start at the same time, their outlet flows to start at the same time, but they may not yield the best outcome from the control perspective. So that leads to our two problems that we considered in this work, and that is the rigid profile input scheduling and receding horizon control under uncertain preview. So next, I'll give a brief overview of the first problem and our approach before spending a little bit more time on the second problem, with the focus of trying to give you some intuition on the high-level understanding of the approach. So first, the rigid profile input scheduling. So the problem stated here with a bit more detail is, given a continuous time, linear time invariant dynamical system and a finite scheduling horizon of length t. So the scheduling horizon is now this continuous interval between 0 and t. And we're given that set of information about the environment, so the rigid profile disturbance inputs and the sensitivity to deviation from the requested timing, as we've encoded in this calligraphic E. And we're also given a fixed nominal control input. And the aim is for the controller to determine the scheduler to determine the best nominal schedule calligraphic n such that the dynamical system of P to the scheduled disturbance inputs and the fixed nominal control input is within the constraints for the entire continuous horizon. Where best here is about minimizing that the user sensitivity for the system. So in relation to our control hierarchy that we introduced, this problem relates to generating this nominal influence only and not how we interact through the controller through these signals F and W, which relates to dealing with uncertainty. And in this system, this setup, we're only dealing with the nominal and also with the nominal control input. So this can be formulated as the following optimization problem, where we have X here is the evolution of the state of the dynamical system in response to a set of rigid profile inputs that have been shifted by a certain amount tau, where Vj are those requested rigid profile inputs. So example, one of them might look like this. And the tau j are actually our decision variables, and that's how much we shift each of these rigid profile inputs by. And the hj are the user sensitivities to the shift, and they formulate our cost or our objective that we're trying to minimize. So there's two challenges, two main challenges with this optimization problem. The first is that the constraints are highly non-convex in these shift intervals. So even though the dynamics are linear in the inputs and the constraints are linear in the state, the dynamics are very non-linear in our decision variables. There's actually a shift on these inputs. And this non-convexity makes it hard to distinguish between global and local solutions. And then the second challenge is that the constraints need to be satisfied for the entire continuous interval from 0 to t. And this leads to an infinite number of constraints. So overall, this type of problem can be classified as a non-convex semi-infinite program. And essentially, our aim is to try and find good, feasible solutions to this program. And the approach we consider is a two-stage approach, where the first stage aims at finding a reasonable, feasible solution on a discretized space. So the first step of this stage is to discretize the decision variables and to make the decision spaces finite. And this is a restriction of the original problem, but has the advantage that at least it can be solved globally, at least in principle, by using, say, an exhaustive search. However, there's much more sophisticated methods that can be used if the problems have a more defined structure. The second step is then to discretize the constraints, again, to be finite. And this is a relaxation of this discretized problem, but it leads to a finite number of constraints, which makes the problem amendable to more standard non-linear programming solvers. And then by exploiting linearity of the dynamics with respect to those inputs, the discretized problems can be formulated as binary linear programs. And these structured problems can be solved globally much more efficiently than using an exhaustive search. So the main challenges with the first stage is to manage the problem size, which is the problem of these binary linear programs. And that means we don't want the discretizations to be too dense. Therefore, uniform sampling of these intervals is not the best solution. The key to, but we also need to ensure that this discretizations are sufficiently rich to ensure that the outcome is actually continuous time feasible. So the key to the approach is to only add the time points of the constraint sets where the most constraint violation is occurring. And to that end, we devise a parsimonious method of discretizing the constraints, but future work is to actually construct a good method to discretization of the decision spaces. So now once we have this feasible schedule, The aim of the second stage is then to improve on the cost with respect to this start-in schedule. And we do that by first restoring the decision spaces to be from their continuous intervals. And then we use a continuous-based method, in this case, a sequential quadratic programming method, to locally improve the cost. So these methods are usually sensitive to initial conditions, especially for this highly non-convex setup. And that's what motivates having the first stage to give us a good feasible starting point to be able to use this method. So the challenge of this stage is to ensure continuous time feasibility throughout the algorithm, to ensure that the algorithm terminates finitely, and that the final schedule is better, or at least no worse, than the initial schedule. So the main result of our two-stage algorithm is that it terminates after a finite number of steps with a schedule that is feasible for that original non-convex semi-infinite program, and is within a tolerance of the optimal for the restricted discretized decision space problem. And as we'll see on the next application or numerical example, this method appears to be tractable for realistic sized problems. So here is an example from that motivating irrigation network application, where we have a system of 10 pools and we have 2 users per pool. So the top figure here shows the requested rigid profile inputs, where each profile input is a pulse with a specified start time, duration, and magnitude. Many of these requested profiles at the start at the same time, and as we'll see on the next slide, that causes the system response to violate the constraints. In this setup, the scheduling horizon is 24 hours, and the scheduling intervals are plus or minus 3 hours. In this setup, the discretization of the decision spaces leads to 24 to the power 20 different possible combinations of the schedule, which makes it completely infeasible to solve by an exhaustive search. Whereas our two-stage algorithm terminates with the schedule that's shown in the bottom figure in approximately 20 minutes. And in this bottom figure, we can see that the shifted rigid profile inputs and these shifts have been made so that the system response is inside the constraints, and they're close to the original as per the user's desire. So here is the actual order level response to both the unscheduled inputs and the scheduled inputs. In the unscheduled case, you can see that there's several points where the constraints are violated, whereas under the schedule determined by our algorithm, then the constraints are all just inside the limits. So this is work that's just recently appeared in this paper in Transactions on Control System Technology, and was done in collaboration with my supervisors and Farhad Faruqi. So next I'm going to discuss the constrained receding horizon control with uncertain preview. I'll give a bit more detail on the problem formulation before discussing a model predictive control or receding horizon approach to this problem. So if we recall our control hierarchy from the beginning of the presentation, this problem looks at the synthesis of the controller with consideration of how to use this model of future disturbances, WT, and also how to limit the evolution of this model by passing this set of constraints to the scheduler FT. In this setup, the dynamical system P is going to be modeled in discrete time. And here, just restating what the controller synthesis problem is, it is to synthesize a controller C that has the inputs, the current state, the current disturbance input, which again, we're assuming in this setup's measured, and this model of future disturbances. The outputs are the control input to the dynamical system, UT, and this signal to the scheduler that is going to be used to restrict how this model of future disturbances might evolve. So the controller should achieve the following, that we want the state and input constraint satisfaction over the infinite horizon, and we also want, as a secondary objective, good performance. So because we're dealing with, again, constraints and uncertainty, we use a well-known approach of using robust receding horizon optimal control, so also known as robust model predictive control, MPC. So restating our aim is to achieve the constraint satisfaction for the dynamics of P over the infinite horizon in the context of this receding horizon approach, that is equivalent to recursive feasibility of the robust model predictive control problem to solve at each time. And the challenge is then, how do we restrict what the scheduler can provide as uncertain preview models at WT of future disturbances to achieve this recursive feasibility? And that is going to be this role, as we've already alluded to, the role of this FT. So what is the preview model that we're going to look at here? Well, the preview model is going to consist of the exact value of the current disturbance dt, and which is measured by, for example, is measured by the meter at the supply point, together with this set WT that is going to be a Cartesian product of disturbance sets across the prediction horizon. So this allows the preview to be structured, time varying, with time correlation across the prediction horizon. So for example, on the left here, we could have the uncertainty set is described as any disturbance between the red and the blue, where you might have some correlation between when the disturbance goes on and when the disturbance goes off. Or a second example on the right here is you might have almost no uncertainty in the immediate or near future, and then further into the prediction horizon, the uncertainty gets much larger. So that leads to the question of, how do we coordinate this preview generation and the control? And the approach that we take here is to only allow the uncertainty to increase at the end of the prediction horizon. And this is how we define this FT, as the set of possible disturbances at the end of the horizon. And that leads to the preview consistency condition, which is stating that this uncertainty at the end of the horizon is the only point that the uncertainty can increase is at the end of the horizon here through this f of t plus 1. Everywhere else in this overlapping region, the uncertainty cannot increase. And this is also consistent with the fact that the start of this preview set, all the uncertainty is resolved by virtue of actually having a measurement of the current disturbance. And since this disturbance measurement only reveals itself at each instance, it also motivates the need to have these sets WT constructed recursively. So for the rest of this work, we are going to make this assumption that we're calling the schedule assumption, and that is, given the end of preview uncertainty set FT, then at each time T, the scheduler S determines the preview update WT plus 1 such that the following consistency condition holds, such that there's no uncertainty added in this overlapping region. So that only leaves this flexibility to add uncertainty at this end of a horizon point through this f of t plus 1, which is left unconstrained. So the question is, well, what isn't desirable end of preview set? Well, a large end of preview set may be desirable for the scheduler, since this gives the scheduler greater flexibility in scheduling future demand, and therefore increasing the likelihood of accommodating all the users' requests and keeping them satisfied. Whereas a small end of preview set leads to less uncertainty in the future, and hence the controller may be able to achieve better performance since it can steer the system closer to the limits. So this leads to a potential trade-off. And again, we're back to this question of how can this trade-off be managed? So now I'll just present what the model for the dynamical system and the form of the controller that we're looking at in this problem. And here, the dynamics are given by a linear shift and variance system in discrete time, where we're given the initial state psi, and we're given the model data A, B, and G. And we've got our control input UT and our disturbance input DT. So the control is going to come from this to-be-designed controller KT, which is an element of this control law sequence, where each element of this control law sequence can depend on the current state, the current disturbance, and the current preview. So in this setup, the constraints are given by these sets YT, which are defined by these linear inequalities. So they're essentially time-varying polyhedral sets, because all these elements that make up the inequality could potentially be time-varying. So now stating the control synthesis problem, it is the recursive synthesis of control law sequence K and the end of preview sets F, such that the scheduler assumption, under the scheduler assumption, that then for all time and the infinite time horizon, the current state, the current input, and the current disturbance is inside the current constraint set. Where x of t here is given by this formula here, which is just the evolution of the system P under the sequence of control laws that were to be generated. Now, just reiterating, since this problem is dealing with constraints pertaining to the uncertain evolution of the state, then we're going to take the well-trodden path of receding horizon optimal control approach. So that leads to the finite horizon optimal control problem that needs to be solved at each step as part of the MPC approach. And that's given here, where P is and ZT are our decision variables, where P is a sequence of feedback policies, where each element of the sequence can be a function of the initial state and the past and current disturbance inputs. The ZT here is a terminal constraint that will be used to achieve a recursive feasibility that we're allowing to be selected or adjusted online. And calligraphic P here are constraints on the decision variables that are derived from the constraints on the dynamical system, and also a set of admissible terminal constraint sets that limit the choices of ZT. And JT here is our cost. Now, in this work, JT, or the cost, plays no role in achieving recursive feasibility. So from now on, we're not going to focus on that aspect. So how does the MPC controller work? Well, first, at the current time t, if the constraint set is not empty, then we select any feedback policy sequence and terminal set in the constraint set. We then assert the control input as the first element of this sequence, evaluated at the current state and the current disturbance. And since this this sequence of feedback policies was feasible, so it was from this set, and this set encoded constraints on the dynamics as well, then we're guaranteed that it will be inside the current state, and inputs will be inside the constraint set at the current time. We then use the selected terminal set to inform the selection of the end of previous set FT. And then lastly, we repeat this at each time instance. So here the question is, well, how can we ensure at the next time instance that the constraint set is not going to be empty? Well, that is the recursive feasibility property, where if the current time instance is not empty, then we can guarantee that the next time instance is not empty. And if this holds and the initial problem is feasible, then we get our primary objective, and that is constraint satisfaction over the infinite horizon. So the two key questions are, how do we make the problem recursively feasible, and how do we select this end of preview set using our chosen terminal set? And the answers are that we restrict the choice of terminal set using the admissible terminal sets T, and we also link the FT to the admissible terminal set as part of ensuring the recursive feasibility. So that leads to the question as to what property should this set TT, which is the set of admissible terminal sets, satisfy jointly with the end of preview set, such that the problem is recursively feasible. And that's given by this result, which is given a feasible policy sequence P and terminal set ZT, and also end of preview set FT, and admissible set of terminal sets T plus 1, then if this condition holds, then provided the schedule assumption holds for the given end of preview set, the MPC problem is recursively feasible. So the middle part of this condition here is about the existence of a sequence of feedback policies P that satisfied the constraints over the next prediction horizon, including at the end of the horizon with respect to some element ZT plus 1 that is an element of the set T plus 1, which is highlighted in the red part here. So now that we have this condition, if we can satisfy this condition, we get our recursive feasibility result. So that leads to the question of, well, how do we now design these TTs so that each end of preview set can be constructed to meet this condition? Well, there's several approaches to how we could do that. And one, potentially naive approach would be to just use static sets and fix these sets across time. So if we're doing this and we have the fixed end of preview set and a set of admissible terminal sets, which we've denoted these fixed sets Z bar and F bar, and they satisfy this control invariance condition, then the recursive feasibility condition on the previous slide is satisfied. Now this has several advantages and limitations. The main advantage is that this is almost a standard control invariance problem. So, it's known how you might construct such sets. And because we're not allowing them to be adjusted online anymore, then these sets can be calculated offline, which leads to a simpler online optimization problem. But there's some significant limitations which relate to how the constraints can be allowed to change over time. So in particular, there's this infinite intersection of the constraint sets inside the condition here, which implies that to even exist such sets, this has to be non-empty. And even if this is small, it may lead to small sets Z bar and F bar, which may lead to very conservative performance for both the control and scheduler. So the idea to overcome these limitations is to actually allow the terminal set to be adjusted online. And we do this by parameterizing the set of admissible terminal sets in terms of additional decision variables. And this builds on the ideas from literature on MPC reference tracking. And here we'll just outline the approach, which is to determine some fixed sets, now we're calling ZO and FO, that satisfy a control invariance condition, where this control invariance condition does not have the requirement on it being in the inside of that intersection of the constraints, the infinite intersection of the constraint sets. We then introduce some additional decision variables, a non-negative scaling parameter sigma, an artificial reference trajectory, and a constraint restriction level. And then third, we parameterize the set of admissible terminal sets TT as scaled and shifted versions of this static set ZO, where the scaling is reference to the scaling parameter and the shifts are the end of horizon points along this artificial reference trajectory. And then lastly, we select the end of preview set, this FT, as the scaled and shifted static set FO corresponding to the selection of the terminal set out of this set of admissible terminal sets. That is, the end of preview set is equal to a shift, where the shift is the end of horizon point along the same artificial reference trajectory that was used to define this Z star, and the scaling is also the same one to define this Z star. So how do we actually make this approach recursively feasible? Well, it relates to ensuring that the artificial reference trajectory, which is used as the shifts for these sets, satisfies certain conditions. And that is that it is consistent with the model dynamics, that the trajectory is eventually periodic, and the periodic part is sufficiently inside the constraints. So this allows us to state the recursive feasibility result, which is assuming the scheduling assumption holds with the end of preview set equal to the scaled and shifted static set, so how we just described we're selecting it, and the constraint set from one time instance to the next time instance does not change too much, then the adjustable terminal and gradient approach is recursively feasible. So note that this condition on the constraints is that it only doesn't need to change too much from one time instance to the next time instance. So this leads to several advantages of this approach. The first is I've already highlighted that the control invariance condition required on these static sets does not have the requirement that it's inside the infinite intersection of the constraints. So that makes it, more choices and less restrictions on how you can choose those sets. Then also the constraint restriction in that recursive feasibility result is only from one time instance to the next time instance. So that means the infinite intersection doesn't necessarily need to be non-empty. And another advantage is that we have these additional decision variables that we can use in the cost to balance the secondary objectives. So for example, the negative penalty, we could put a negative penalty on that scaling parameter sigma, and that will encourage large terminal and end of preview sets. So the remaining challenge is to actually make the problem, the optimization problem, tractable. So there's two aspects of the problem that as currently formulate that make it intractable. And the first is that these decision variables P, the sequence of feedback policies, are infinite dimensional decision variables. The second challenge is that we have an infinite number of constraints. And there's two sources of the infinite number of constraints. The first is that we've got inside the definition of P, this robust constraint condition that we're having to satisfy the constraints for all possible future realization, finite horizon future realizations of the disturbance. And the second source of the infinite number of constraints is that we're requiring the artificial reference trajectory to be sufficiently inside the constraints. So we take use some common techniques to overcome these issues. And the first is that we parameterize the policies, the feedback policies, to be affine in the current and present disturbances. So that leads to finite dimensional decision variables, where our decision variables, instead of being arbitrary feedback policies, become these parameters K. The second step that we take is to restrict the preview sets to be from a class of closed convex cones, and restrict that the static set that we use in the approach to be polytopic. So this allows us to use some duality-based robust optimization trick to replace the infinite constraints with equivalent set of finite dimensional ones. And the overall result is that we end up with a finite dimensional set of convex conic constraints that is equivalent to the restricted version of the original problem. That is, solutions to this finite dimensional problem are feasible for the original problem. So I'll now go into a second application and a numerical example on this application, that is a two-vehicle platoon. So in this setup, we have a lead vehicle and an ego vehicle, where the lead vehicle acts as the scheduler and provides to the ego vehicle a measurement of the current velocity and a preview of the future velocities. The ego vehicle, which acts as both the dynamical system and the controller, and as the controller, it passes back to the lead vehicle limitations on the future velocities through the signal ft. In this setup, the environment is the road conditions, the road signs, and other users on the road. And we have the control input is the acceleration to the ego vehicle. And in this setup, we have the constraints on the acceleration, the relative distance between the two vehicles, and the relative velocity between the two vehicles. And the overall performance goal is to minimize the distance between the two vehicles while providing the lead vehicle with some flexibility to adapt to the environment. So this figure here shows 100 different trajectories of the velocities of the lead vehicle. And as you can see, there's some periods where there's smaller uncertainty in the velocity, and then some periods, say around the 70-second mark, where there's larger uncertainty in the lead vehicle's velocity. And then there's also periods where it's known that the lead vehicle is accelerating, and then there's periods where it's known that the lead vehicle is deaccelerating. So I'll just now switch to a small animation of a response to one such trajectory, the control response to one such trajectory. So here we have the top figure that shows the two vehicles, where the green is the lead vehicle and the blue is the ego vehicle. And these dashed lines are the constraints on the position of the ego vehicle. The middle plot is going to show the velocity of the two vehicles, and the bottom plot is going to show the relative distance between the two vehicles along with the constraints on the relative distance. So as we'll see in this setup, the constraints are actually going to change at different time instances. And in fact, the intersection of the constraints over the simulation horizon is empty. And we'll see that just before the constraints change, the ego vehicle will back away from the constraints because it has a preview of what's going to happen so that it doesn't violate the constraints. And we'll also see, say, around the 13 to 16 second mark, that the ego vehicle will back away from the constraint as well, because that's that period where there's larger uncertainty in the velocity of the lead vehicle. So you can see when there's little uncertainty, it tracks pretty closely to the constraint, and then when just before the constraint changed, it backed off. And here there's a bit of large uncertainty, so it backs off, and then at the very end, there's almost no uncertainty, so it's almost tracking right on that constraint limit. So I'll now just switch back to the slides for the last bit of the presentation. Yeah. So this figure here shows that signal FT that's provided to the lead vehicle. So each of these bars here are the ranges of velocities that the lead vehicle could schedule at a future instance. And it just highlights that there's some periods where the bars are quite large, and then there's some periods where the bars are quite small, and these usually correspond to when those constraints are just changing. When the constraints are changing by, a lot, then, the controller's telling the lead vehicle, I need very little uncertainty in the future to be able to accommodate this. So I'll now just give a brief conclusion and some directions of future work. So in conclusion, we considered two problems associated with the synthesis of the scheduler and controller in the control hierarchy that we set up in the first part of the presentation, where the first problem was dealing with determining this nominal schedule that will influence the environment, and it was this rigid profile input scheduling. And it was a difficult scheduling problem because we had the constraint on the profile inputs being rigid, and it was also because of the continuous dynamics. We proposed a two-stage method using discretization to yield good feasible solutions. So the second problem we looked at was a controller synthesis problem that also looked at using an uncertain preview of how the environment's going to respond to this influence. So it was difficult to guarantee the feasibility while allowing this preview to be structured and also deal with the time varying constraints. And we proposed a receding horizon control method that used adjustable internal ingredients to achieve feasibility while also allowing some flexibility in how the cost can be chosen, which may be used for managing secondary objectives. So just to outline some potential directions of future work, so in the lines of problem 1 is to explore and prove methods for choosing the restricted decision spaces to achieve better and faster results. So we propose a good method for choosing the discretizations of the constraints. So future work would be also doing determining a method for discretization of the decision spaces. In the lines of problem 2, we have two potential directions of future work. The first is to explore how the cost can be chosen and updated from one time instance to the next so that we can meet certain secondary objectives such as performance optimization or stability, for example. The second direction along the lines of problem 2 is how we could exploit structure within the optimization solvers to enable scalability of our approach to large systems, especially for systems that have a spatial cascade structure like we saw in that irrigation network example. We could also extend these, work to extend these results to more general system dynamics other than the linear time invariant systems that we've looked at here. And lastly, as outlined, there's future work to explore the problem of how we generate these uncertain preview sets, based on how the environment will respond to this nominal signal, and also meet that scheduler assumption. That is, you know, given this signal from the controller, ensure that we don't add uncertainty in the overlapping areas. So that concludes my talk. So thank you. I'm happy to take some questions.
Thanks, Ade. Is there any question for Ade? We have time for one question. Okay, let's see. Okay, isn't any question now? If anyone comes up with a question, please contact him via email. I think he will still check his email for some time. Thanks again, Ade, for the talk. Thanks, everyone.
Yeah, thanks, Ivan.